So let me just make some corrections first. So yes, in yesterday's talk, so there was some point when I wrote the inequality in the opposite direction. So in a lemma where I prove that the T is injective, somehow I wrote something like this. So the mu, so because mu H F, I wrote something like this. But this is incorrect. That should be this way, okay? Because this is the smallest dilatation. But the argument is the same. So just, what we did is just so this is just so we obtain the inequality in both directions. So that if I change this to that, then the next one is also be changed to the other direction. So we get the equality. So the argument is all right. But I just wrote like that, and that was incorrect. So that should be this way. Okay. And the other correction is about this is more non-trivial. So the next one is a statement of the infinitesimal Roydens theorem. So well, probably it's better to write it again, because this is also what I'd like to talk about in the first half of this talk. So this is the Roydens infinitesimal version. So you have a K, which is linear isometry, also complex linear isometry between two spaces of the holomorphic quadratic differentials. One is that on sigma 1, and the other is on sigma 2. Okay. And then what I wrote is that there exists by holomorphic map, by holomorphic homeomorphism from sigma 2 to sigma 1, which should be written by H, such that the Kf of phi is always equal to the, I wrote something like this, but I forgot to put the constant here. So and the constant, which is a complex number with absolute value 1. So I forgot to put this yesterday, but the statement should be like this. Okay. Right? Any question? Is it okay? Is it clear? So the proof of this theorem is fairly complicated. And if you would like to study this, the proof, then the only way is to just read the original paper by Royden. So in a textbook I introduced yesterday, so that Imayoshi Taniguchi, they mentioned this theorem, but without proof. So to understand how you can prove this, then you have to still you have to read the Royden's papers. But let me just sketch how this is proved very intuitively without filling the details of the argument. So, so what you have is just a map between two cotangent spaces, okay, and of the Teichmüller space, the space of the quadratic holomorphic differential, and then isometry means isometry with respect to the norm. So we call that norm was just the integration of this form on sigma. So the norm on sigma 1 is something like that. Okay. So that this means that norm of the phi should be equal to the norm of k of phi here. So because k is norm preserving, we see that holomorphic, any holomorphic quadratic differential with zero means that the point where the value of the phi is 0, with zeros, probably the plural, zeros of the degree 3g minus probably 4. Okay. Is mapped to the same kind of holomorphic quadratic differential by k. So this is quite a non-trivial statement. So the degree of 0 is something like that. So if you you have a, so you remember that the phi, at the 0 of the phi, the coordinate system is patched with singularity like that. For instance, this is the smallest 0 with smallest degree. Okay, and the 0 with larger degree can be. Oops, sorry. This should be the patching of the. Well, I cannot write it in a good way, but so this is the patching of the free Euclidean coordinate at this point, and this is 4 Euclidean coordinate. So the degree, so this should be something called the degree half of a degree 1, depending on how you think of that. But anyway, so the degree should be probably 1, the degree 2 or something like that, or degree 3 probably. The degree, wait a minute. So the 0 of the degree 1 should be the good way to call it. Anyway, so the degree can be interpreted like that. So that in a sense that if locally if the phi is written like some function phi psi xi probably, that this is a holomorphic function. If phi can be written locally like that, then it means that degree 1 0. And if it's something like that, then degree 2 0 or something like that. Okay. So if you have more z, and this is a local expression at the point 0. So if you have a z twice, then you have degree 2, and then something like that. So that's a degree of the 0. So you just consider the expansion of this function, Taylor expansion, and because it takes the 0 here, so the Taylor expansion starts from the second term, so that it has a z something. So you can divide it phi by z, and you have a still holomorphic function. So this is the degree 1, 0. So if you start from the third one, then you can divide the function by z again. So this is degree 2, 0. Okay, so that the naming is something like that. So if you have a 0 with this high degree, so if you have genus 3 here, so that's a degree 5, 0. Okay. Then you can show that the image of so if this is norm preserving, then such a the holomorphic differential with such a high degree 0 should be sent to a holomorphic differential with high degree 0. So that can be proved by very subtle computation of the norm. So, why do we choose 3g minus 4 here? Because if, for instance, if g, so we first considering the case when g is greater than or equal to 3. So in g equal to 2 case is exceptional. So we have to need we need another kind of argument to deal with the case when g equals 2. But suppose g is greater than 2. Then if you have a 0 of this degree, then you cannot have 2 of them. Just you can just have 1 such a 0 with a high degree. Because there's a Euler-Poincaré theorem saying that the sum of the degrees of 0 is should be equal to the 4g minus 4. I'm not sure that it is correct. When g is 2, it's 2, and g 2, oh, yeah, that should be correct. So, so the sum of the degree of 0 should be this, because this is a kind of the classical theorem of the Euler-Poincaré. And if you add the degree of the zeros, then you have something times, actually minus 2 times the Euler number of the surface. So that should be something like this. So that means if you have this 0 of a high degree, if g is greater than 2, then there's only one such a 0. So if genus is 2, then this number should be 6 minus 4, so it's 2. And this number is 8 minus 4. So you can have two zeros like that. But if g is greater than or equal to 3, then you cannot have 2 of them. So that's why there's a unique 0 with degree greater than or equal to 3g minus 4. Okay? Now I will show you how to construct well, it's a biholomorphic map from sigma to sigma 1, but it's okay to just construct a holomorphic biholomorphic map from sigma 1 to sigma 2. It's the same, just take the inverse. So if you have a sigma 1 and choose some point there, and you consider, you consider a holomorphic quadratic differential whose 0 with high degree is exactly this point. So that should be phi x. It's not so difficult to show that for any point, you can have a holomorphic quadratic differential whose highest 0 is exactly that point. Now, K takes this map to some quadratic differential in sigma 2. Okay. Now, because of this lemma, so I should have, so this should be lemma. Because of this lemma, this psi has unique 0 with degree greater than or equal to 3g minus 4. So you have a point y on sigma 2. So then send this x to this y. And you can show this is holomorphic. So it's easy because this is just a point of the 0, then it moves holomorphically. And actually, for this h, this equality holds. So this part, you need some proof, but it's not so easy, but you should prove that. So the step is something like that. In the first lemma, you show that the holomorphic quadratic differentials with with 0 or with high degree is the set of such holomorphic quadratic differential is preserved by norm-preserving map K. And then we can construct a map taking 0 to 0. So that's so for any point, we consider the holomorphic quadratic differential having 0 at that point, and send it to the 0 of the image of this holomorphic quadratic differential by K. Then you get the holomorphic map from sigma 1 to sigma 2. And you can show that this equality holds for such a map. So that's what Royden did. Okay.
That is from
sigma 1 to sigma 2. So I defined the sigma 1 to sigma 2. But so the inverse of this should be this h. So I should write it from sigma 2 to sigma 1. And well, this is the same, just the same construction. Sending so choose some point on sigma 2 and consider the holomorphic quadratic. But then I have to use K inverse instead of K. So the proof is something like that. Okay. Now, and now I will explain why this infinitesimal version of Royden's theorem implies original Royden's theorems. So first, let me remark that the norm on QH sigma 1 is just the norm induced from the Taihi-Mura distance. what do I mean by this? So so if you have so let me recall that the tangent space of Teichmüller space at this point. Probably I put sigma 1 or I can put 1 here. So is identified with such things. So the R, where phi is a quadratic differential, then R is from 0 to infinity. So when R is 0, everything is identified to 1 point. Okay. And the natural sorry, that R, sorry, R is not in 0 1. But if I put R as a number in a 0 1 interval, then it's just a complex dilatation. But because we are considering the length in a Teichmüller metric, and so we changed the parameter. So K was written like exponential of 2t minus 1 over exponential of 2t plus 1. So that means this R can vary from 0 to infinity. So the R should be in 0 to infinity. And this is the parameter of the geodesic, which I introduced yesterday. So if R is 1, this is just the speed 1 geodesic. So the tangent vector of the speed 1 geodesic. And if R is 2, then speed 2 geodesic. So that's what I mean. So then the norm on the tangent space. So norm on the tangent space. Tangent space should be this R. That's a natural thing to expect because if the geodesic, if something proceeds on the geodesic with some unit speed, then its norm must be 1 if you consider the Finsler metric and, with respect to that structure. So that should, if its speed is R, then the norm should be R. Okay, that's a norm induced by Teichmüller metric on the tangent space. So how can we define the norm on the cotangent space? So the natural, there's a standard way to define that which is the usual definition. Is a supermum of the pairing with the tangent space. So that this should be tangent space, TS. And consider the vector of the norm 1. Okay. And actually, this should be just the product. So so this is something like this. Phi is quadratic homomorphic differential. Okay. And the supermum. Okay, So you have to quadratic differential and taking something like that. But the absolute value of this one is always 1. So, sorry. You have to take the absolute value of that. Then that should be, because the absolute value of this one is 1, always 1. So this should be smaller than or equal to this one, okay? Right? Because the absolute value of this is 1. Right? And the equality holds when sigma, these two are the scalar multiple. Okay. So that means sorry, this should be again, this is always like that, but if you take a supremum, then psi can be phi because you are taking a supremum. If we let psi be phi, then what you get is just something. Oh, sorry, the absolute value is here, right? Okay, so if we let psi be phi, then what you have is something like this. So because this is a square of the absolute value, it's just a psi. So you have an inequality with the opposite direction. So they should be equal. So that what we have is this is just so that's why we define the norm by this. So this norm is the norm induced by Teichmüller metric. Okay. Now, let me show you how we can prove the Roydens theorem from the infinitesimal Roydens theorem. So, so you have so the setting is like this. So in a Roydens theorem, so what you are given is isometry f from the Teichmüller space with Teichmüller metric to itself. And what you have to show is you have to show is that this comes from some mapping class. Okay. Now this implies this map induces a map between the cotangent space of Teichmüller space. Okay. So maybe the direction should be reversed, but this induces the map from cotangent space of at fx to the cotangent space of at x. So you have isometry, and so the cotangent vector can be pulled back by isometry, and then you get the cotangent vector, so at the original point. So that you have a map like that. And because f is isometry, this preserves norm. Because norm is determined by the metric, so that this should be norm preserving. Okay. So you have a linear map between these two, which preserve the norm. And then, so you can use this theorem and to show that there exists H. Well, I wrote from sigma 2 to sigma 1, but probably taking an inverse, now it's better to write it this way. Because now we have a map from the, sorry, that X is sigma 1 F1, and we write F of X is sigma 2 F2. Then this is a map from the cotangent space at sigma 2 F2 to sigma 1 F1. So this should be reversed. So what you get is a map from sigma 1 to sigma 2. Okay. And this H induces this linear map. Okay. Now, we consider the action of the mapping class. So we define an element of mapping class as a one represented by this map. So you have a H. So you have F1 H, then F2 inverse. Then this is a map from S to S. Okay. So then, okay. Then we just consider sigma 1 and F1 gamma inverse. Okay, so that was the action of mapping class. So if you just compose the inverse of that from the right, okay, then what you get is sigma 2 H F2 inverse. Okay. No, not sigma 2, sigma 1. Sorry. So recall that sigma 1 and sigma 2 are bihomorphic, but the marking has changed so that H sends sigma 1 to sigma 2. So if you put H here, then this is the same as the marking on the H sigma 1 with, sorry, there's no inverse here. Okay, this should be the, okay. Wait a minute, this should be H inverse. H was, F2 was a map to sigma 2, that should be H inverse, sorry. So and this should be the sigma 2 F2. Okay. So sigma 2 should be identified with sigma 1 by H. So this direction. So if you change the marking like that, then these two are bihomorphic. So just this marking on this means the marking on this place. Okay. So now we have gamma and we have F. Both of them send sigma 1 prime sigma 1, the pair of sigma 1 F1 to sigma 2 F2. Okay, the maps this point to the same point. So that is what x1 and x2. Okay. And also, the map induced on the cotangent space is the same. Now, Tajimura space is a geodesic space, so every 2 points can be connected by geodesic. So if these two are equal, also they induce the same map on the tangent space. So you have two isometries. So these are isometries. F is isometry by assumption, and as I showed yesterday, the mapping class group action is isometry. So you have two isometries. Both of them take 1 point to some point, and they induce the same map on the tangent space, and the space is geodesic space. Then they have to be equal. Gamma means the action of gamma. So it's isometry. So that's a standard argument, okay? So if you look at so in a geodesic space, if the map is the same at 1 point and the tangent space, then they have to be equal, right? Every point can be joined to that point by a geodesic. And the direction of geodesic should be preserved so that they are the same. So that's the proof of the Royden theorem from the infinitesimal version. Okay. So okay, somehow I spent too much time on this, but so on the last day, Wednesday is the last lecture. So on Wednesday, I'd like to show you an analogy of this Royden's theorem with respect to the Thurston's asymmetric matrix, which is actually what Adanaze and Ifan and I proved. So so this is a kind of the introduction of the last day's topic. But anyway, so Royden's theorem can be proved like this from the infinitesimal version. Now, in the remaining 20 minutes, I'd like to show you an analogy of this kind of argument or this kind of result in a different object. That's what's called a curve complex. So curve complexes and their automorphisms. So section was 3. So this is rather combinatorial object. So it's closer to for instance, the Cayley graph or the tree or something like that. So which is dealt with in other lectures. So so S is as before the closed surface of genus greater than 1, and CS is something called a curve complex. The curve. So I will define it. So it's a simplicial complex whose vertices are isotopy classes or homotopy classes of simple closed curves on non-contractible simple closed curve. So we ignore the contractible homotopic to 0 curves, and we consider the isotopy classes of simple closed curve on S, So you have, of course, infinitely many such objects. So they are all the vertices of this complex. And so, you suppose you have n vertices. Well, probably n plus 1 would be better. So from 0 to n, so n plus 1 vertices. These vertices span an n simplex if and only if they are realized by disjoint, this is important, disjoint simple closed curves. Let me draw some picture to help your understanding of the definition. So for instance, you consider genus free surface and consider simple closed curves like this. So you have one here, one here, one here, one here. So they are disjoint. Okay? So you have 4 vertices which are realized by disjoint simple closed curves. So you have 3 simplex. That's a tetrahedron spanned by these 4 points. So these span such things. Okay? Now, if you change this V3 to another curve, V 1, 2, 3, 4, probably. 0, 1, 3, sorry. Then so V4 and V3 are not disjoint. So you cannot make them disjoint by isotopy. They intersect essentially. So then this vertex V4 should lie somewhere like that and span but V4 is disjoint from all the other 3. So you have another 3 simplex. So that the tetrahedron spanned by these 4. But there's no 4 simplex spanned by these 5 vertices. Oh, this is because this is so. If the parallel, this is because the isotopic class. So if they are they're parallel, they're the same point. Okay. Oh, distinct vertices. Okay. So that's the definition, okay? And so it's easy to see the mapping class group acts on this object by simple automorphism. So if you have you have mapping class group. So for any, so you have a vertex in CS, then it corresponds to some simple closed curve, probably C, simple closed curve on S. Then if you have a element of mapping class group, then you can send it to another simple curve by that map. So only the isotopic classes matter. So so if if two curves are isotopic, then these two should be isotopic, and also if the f is isotopic to another map, then this curve is isotopic to that one. So that this can be defined in a good way, and so that this gives an action of mapping class on CS. And of course, disjointness is preserved by the homeomorphism. So if some n plus 1 vertices span a simplex, then that should be the image of those vertices also span a simplex. So that gives simplicial automorphisms. Okay. So this simplicial complex is analog of Teichmüller space, and actually combinatorial version of Teichmüller space, and so this action corresponds to the action of mapping class group on the Teichmüller space. So what I'm going to state here is an analog of Royden's theorem in this setting. So that was proved by Ivanov and Kolkmaz and Luo. So the original version was Ivanov in the case when the surface is closed and the genus is greater than or equal to 2. So in our setting, the Ivanov theorem would be enough. So they show that mapping class group is equal to probably the genus is greater than or equal to 3. That would be better. Okay. Then mapping class group of S is equal to the group of simplicial. This is the group of simplicial automorphisms of the curve complex of S. So our definition of mapping class group contains the orientation reversing. So when I talk about orientation preserving one, then I put something like asterisk. So this contains the orientation reversing one. Okay. So and it's easy to see. You have an injection. So every element of the mapping class group induces our automorphism. And if the automorphism, the image equal, that means all curves. So you know the image of all curves. You have a information on the image of all curves. Then it's easy to see that they should be the same homeomorphism. No, the same mapping class. They should be homotopic to each other. So the injectivity is easy. So injective embedding of mapping class group into the automorphism group. So what's difficult to show is the surjectivity. So in the remaining 7 minutes or something, I will show that how the surjectivity was proved by Ivanov. So you take any simplicial automorphism of curve complex and try to realize it by mapping class. So what we know is that phi preserves the disjointness of simple closed curves. So if because it's a simplicial automorphism, so if two vertices span an edge, then its image also, their image is also span an edge. So that means if two simple closed curves are disjoint, then their image should be also disjoint. Okay. But what he tried to do next was the following. So if you have two simple closed curves, well, which are non-contractible, and the intersection number is 1. Intersection number is so if you have two curves, you can isotope them and try to realize them so that they intersect at the smallest number of points. Then that's the intersection number. So suppose the intersection number of these two curves is equal to 1. Then this condition should be preserved by phi. So this is the main step of the proof, actually. So this can be done by a picture like this. So if you have, for instance, suppose you have two simple closed curves, C1 and C2 intersecting at one point. This is the condition here. Then you can draw other simple closed curves, like system of simple closed curves like this. So you just draw C3 here, and then C4 should be here, and what's next? And the C5 should be somewhere here. So what are they? So the C1 intersect C2 at one point, but the C1 is disjoint from C3 and C4. And then what about C2? C2 is disjoint from C4. And C5, so C2 is also disjoint from C5. Okay? And C3, this one, is disjoint from C1, and then disjoint from C5. Okay, that should be all. So C4 and C5 intersect. So you have these condition of the disjointness, but all the other curves, all the other pairs of curves intersect each other. So that so you have condition like that, and all the other pairs, all the other pairs among the pair of curves in this picture intersect, essentially. Okay. And furthermore, this C4, curve C4, this one. C4 cuts a torus with one hole from S. Okay? Actually, you can show the disjointness is preserved by phi, and the condition that some curve cuts one whole torus from the other part is also preserved by phi. Because if the phi cuts one whole torus, then in one whole torus, all the curves, all pairs of curves intersect. So this condition is preserved phi, and so if you have if C4 cuts S into two connected components, then also that condition is preserved by phi. So the condition that this curve cuts one whole torus from S is preserved by phi. Okay. So this picture should be preserved. That means in particular, the image of C1 and C2 must have intersection number 1. Okay. So that's the point. That's what I proved here. Now, if the condition of the disjointness and the intersection number 1 is preserved by phi, then now it's easy to show that it's induced from mapping class. So because if you have a closed surface, then you can consider the system like this, so that so everything intersects at one point over here, and over here. Oh, sorry, this should be the same as this one. So this start here, then start here like that. Okay. Okay. So what I draw here is just a system of simple closed curve intersecting at one point or disjoint, and decompose the surface into a simply connected region. Then because the disjointness and this condition is preserved, this picture should be preserved by phi. So if you have a system like that, then the image of these curves should have the same kind of system. Then you can construct a map from there you have a self map of the surface by here, and because on the simply connected domain, if the boundary is determined by the map, then there's only one way to extend it to the region by Alexander's trick. So that means so there's a unique homeomorphism inducing the changing of this system by phi. So that's how Ivanov proved this theorem. Okay, so this should be regarded as a combinatorial analog of the Ryden's rigidity theorem. So I just overran time. So thank you very much.